Today we're going to take a look at expressing square roots, and not cube roots yet, but just square roots as whole numbers, but then also simplifying square root expressions, writing them in simplest radical form. So a couple of things we want to go through are perfect squares. So we can go ahead and write these down. A perfect square is a whole number whose square root is an integer. And then we can write down our first 12 perfect squares. The first perfect square is 1, because 1 times 1 is 1. Then we have 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 9, 9 times 9, 10 times 10, 11 times 11, and 12 times 12. Those are your first 12 perfect squares. A square root, and I just need you to copy down the first part, is the inverse of squaring a number. It's just kind of going backwards. If you have a perfect square, do you know what number you used to multiply by itself to receive it? So if we take a look, it says find the square root of 36. Well, let's see, what times what equals 36? 6. What's the square root of 49? 7. What's the square root of 144? 12. 3 times 3 is equal to the square root of 9. What's the square root of 9? It's 3. It's important to memorize those first 12 perfect squares because they'll be used quite often. We can estimate square roots by finding the number closest to the perfect square. So let's take a look. It says estimate to the nearest whole number. If we were to put this in our calculator, we would get a decimal. So let's see if we can estimate which whole number the decimal is closest to. So when I take a look at this perfect square, it's almost the square root of 36. So what whole number would be closest to the square root of 35? The answer to that would be 6 is closest. So it's somewhere in between 5 and 6. Let me take a look at the next one, the square root of 55. Okay, let me think of my perfect squares that are next to 55. That would be 64 and 49. 55 is closest to 49, so the approximate or the estimate would be 7 because the square root of 49 is 7. And I did those squiggly lines there to mean approximate. The square root of 100. Well, the square root of 99. What two perfect squares are closest to it? I gave it away. 189. Well, 100 is certainly the closest. So the approximate square root of 99 is 10. The symbol, that little square root symbol, is called a radical. The number inside the radical sign is called the radicand. And when we take the square root of a number, by default, that symbol there doesn't always have to have the little 2 on top. We know that that's called square rooting. We're looking for the perfect square. That's equivalent to the square root of 4, which is 2. There's a couple of things when we're working in this unit. We're simplifying radical expressions. And what that means is that we can't have any perfect squares other than 1 in the radicand. So no perfect squares under the radical. No fractions under the radical. And no radicals are going to appear in the denominator of a fraction. If we have these things, then there's some steps we can do to control it. The first thing we're going to take a look at is the product property of radicals. It says the square root of a product equals the product of the square roots of the factors. So if I have the square root of AB, I can break it up into the square root of A times the square root of B. For example, if I have the square root of 4 times 9, I can break that up into the square root of 4 times the square root of 9. And then I can take that further. The square root of 4 is 2, and the square root of 9 is 3. So that value is actually 6. And if you take a look at 4 times 9, that is 36. So that makes sense. We also have the quotient property of radicals. And that's the same thing. If you have a fraction in the radical, you can break it up into a radical on the top and a radical on the bottom. So we'll take a look at this example. If I have the square root of 36 over the square root of 4, I can break it into two radicals. Square root of 36 on the top, that's equal to 6. The square root of 4 on the bottom is equal to 2. And then I can simplify this further to get 3. We're going to take a look at the prime factoring method of simplifying square roots. And we're going to take a look at these two examples here. The first example says reduce, it might even say simplify, the square root of 24. We're going to use that product property rule to break up the 24 into manageable pieces. So we're going to use prime factoring. So prime numbers are numbers that can't be divisible by anything other than 1 in itself. So some prime numbers that we have are 1. Oops, my pen went, there we go, 1. 2 is a prime number. 3 is a prime number. 5, 7, 11. Those are some good ones to start with. Usually these are going to take care of it. But when I look at the square root of 24, I want to look for a prime number. And I can choose either 2 or 3. I'm going to choose 2 this time because a lot of us like to start with 2 as we're factoring. So I'm going to do a factor tree. So 2 times 12 is equal to 24. Now I have to look at my numbers here. 2 is a prime number, but 12 is not. So that means I have to keep simplifying. 2 times 6. Okay, I know 2 is a prime number, but 6 is not. So I'm going to keep going. 2 times 3. Okay, all of those little numbers there are prime numbers. I'm going to go ahead and circle them in orange. These are all prime numbers. So I'm going to go ahead and write my radical with all of these little prime numbers like this. And I'm going to look to see, hey, do I have any pairs? And right here I do. So let's go ahead and multiply 2 times 2. What is it? It's 4. What's the square root of 4? It's 2. Let's take a look at what else I have under the radical. I have a 2 and a 3. Are they pairs? Are they matching numbers? They're not. So even though I can multiply them, I can't take the square root. It's already simplified. So my final answer to this problem is 2 radical 6. And now I know that may look more complicated than the square root of 24. This is the simplified version. You took out whatever perfect squares there were out of the radical and you put them out in front. Anytime we take a perfect square out of the radical, we can put that number out in front. So we're going to try the next one together as well. So the first thing we want to do is prime factoring. So I'm going to think of some prime numbers. I know 2 goes into 32. It's 2 times 16. A calculator will help when you're looking for your prime numbers. I can take this further. I can say 2 times 8. 8 can be broken into 2 times 4. 4 can be broken into 2 times 2. I'm going to go ahead and circle all my prime numbers. You know you're done factoring when you only have prime numbers left. So that's a whole lot of 2's. So let's see, I'm going to put all of them under the radical. I have 1, 2, 3, 4, 5 of them. And again, I'm looking for doubles. I'm looking for pairs or 2 of a kind because we're talking about square roots. And if you remember, perfect squares when I take the same number and multiply it by itself. So I have that here. I have the square root of 4. What do I have here? I have the square root of 4. And then I have a single 2. That's going to stay under the radical. All of these radicals are being multiplied because that's the product property rule. So now I can start taking the square roots. I know the square root of 4 is 2. Bring down your multiplication sign. I know the square root of 4 is 2. Bring down your multiplication sign. Square root of 2, because I can't take the square root there. But 2 times 2 is 4, radical 2. and we have a simplified value. Let's take a look at some practice problems. The first one is the square root of 81. Sometimes you won't even have to do that prime factoring if you recognize your perfect square. So the square root of 81 is 9, because 9 times 9 equals 81. Let's take a look at the next one. Got the square root of 48. Again, I'm looking for a prime number that goes into 48, and I usually choose 2 to get started. I got 2 and 24. I've got 2 and 12, 2 and 6, 2 and 3. I'm going to circle all my prime numbers, and they're all going to go under a radical. I have 1, 2, 3, 4 2s, and a 3. I'm looking for doubles, so I can put them under the radical as a perfect square. And then I look to see those perfect squares and take the square roots. So the square root of 4 is 2. Bring down your multiplication dot. The square root of 4 is 2. Bring down your multiplication dot. The square root of 3 we can't touch. It's already a prime number. So 2 times 2 is 4, radical 3. The whole number will always go out in front. All right, let's take a look at the last one, the square root of 75. 2 doesn't work this time, so I'm going to pick something else. I'm going to say 3. 3 times 25. All right, 3 doesn't work here, but 5 does. 5 times 5, and that's as far as I can go. So I'm going to go ahead and circle my prime numbers. That just draws my attention to them, and that's what I need to put underneath my radical. I look for doubles. Here they are, or 2 of a kind, and sometimes they may not be written next to each other. That's okay, you're just looking for 2 of a kind. So I have 2 5s, and I know this 2 5s multiplied is 25 times the square root of 3. I always put my perfect squares out in front because when I take the square root, that whole number should be out in front of anything left under the radical. And that's simplifying radicals.